Okay, welcome to today's archive chat. This is the origin of modern astronomy, and you'll have to excuse me today. I have a little bit of a cold, so if you hear some sniffling, um, again, I apologize. In any case, we're going to look at some of the historical events, some of the people who were responsible for establishing um, what we know now today in terms of astronomy. Um, Most importantly, the changes that took place in the different models that we had of the universe around us. So, as we go through this, we're going to look at ancient astronomy, astronomy from very early civilizations and even in prehistoric times. Look at the ancient Greek contributions, including the work done by Aristotle and Ptolemy. And of course, there was a very long gap in time before a lot was done in changing the model. What we don't cover here is in the Middle East and the eastern parts of Europe, there still was quite a bit of work done on astronomy, especially cataloging different stars. In terms of the overall model of the universe, it wasn't until the time of Copernicus that some of these old issues were revisited and our model of the universe was changed. We'll talk about Tycho Brahe. Tycho, although he didn't believe in a sun-centered universe, did make many important contributions to observational astronomy. Galileo was really the champion of the heliocentric model. He supported Copernicus's ideas that the sun was the center of all motion rather than the earth being the center of all motion. We'll talk about Kepler, who you know, also reinforced these ideas, but also discovered that the objects moving in perfect circles was not really the reality, that objects moved in ellipses, planets moved around the sun in ellipses. And finally, Newton, who puts everything together by coming up with his universal law of gravitation. So starting with ancient astronomy. Ancient astronomers, of course, used the heavens to keep track of time. Here's sort of a picture, a drawing, if you will, of Stonehenge. And Stonehenge was basically a timekeeping device. It was a device that was used the shadows of the sun to determine important events. Some of these events were minor in terms of the sky. Some of them were very important, such as the solstices and equinoxes. And this is very important to the ancients, especially the prehistoric peoples, because they heavily relied on agriculture. And if you planted your crops at the wrong time or harvested at the wrong time, not only were you going to, affect your yield, you could, basically put yourself into a position where you were on the verge of starvation if you didn't have enough food. So, keeping track of time was really one of the initial big applications for astronomy. And again, this is extremely important for agriculture. Now, the ancient Egyptians used their astronomical knowledge to predict the arrival of the seasonal floods. But they also began to connect their observations and their cosmology to religious events, or to make connections to their own religion. Very interesting example of this is the air shafts in the Great Pyramid of Giza, which were originally aligned with the constellation Orion and Sirius. And these alignments would take place, I believe, at the time of the pharaoh's birthday. And they were supposed to provide connections to the afterlife for the pharaoh. So certainly the ancient Egyptians had a lot of knowledge about astronomy. So did the Babylonians. They kept very precise records of the heavens, and this knowledge included events such as lunar eclipses, solar eclipses. And it was Thales, later on in ancient Greece, who's said to have used this information to predict eclipses. One myth has Thales really considered to be the first of the Greek philosophers, predicting an eclipse and using that information to prevent a war. However, that's probably unlikely. What Thales basically did was he visited both Egypt and Babylonia and took a lot of this astronomical knowledge back with him. And it was the ancient Greeks who really pushed the idea that it is possible to understand the world around you and make predictions as Thales had made. Later on, other ancient Greek astronomers such as Eratosthenes, who was part of the Greek culture. Eratosthenes actually was part of the Macedonian Empire, or what had been the Macedonian Empire. He was able to determine the size of the Earth by making a very interesting set of observations. He observed in the Egyptian city of Alexandria, named after the great Macedonian conqueror, Alexander the Great, that on the summer solstice at noon, a shadow cast by any object would make about a 7.2 degree angle. He also noted that in the city south of there, which sits on the Tropic of Cancer, Syene, which is the current location of the Great Aswan Dam in Egypt on the Nile River, that the shadows would disappear. That if light were shining down a well, it would shine all the way to the bottom because the sun would be directly over above during the summer solstice at noon. Now, by comparing these two angles, this 7.2 degrees and this 0 degrees, he noted that the distance between the cities was, I think, approximately 800 kilometers, and that this made a fractional distance of the total circumference of the Earth, just as 7.2 degrees was a fraction of the total 360 degrees of the Earth. So using this simple geometrical relationship, Eratosthenes was able to determine the circumference of the Earth, and he was therefore able to measure the Earth indirectly. So again, this sort of reinforces the idea that the Greeks had, that it's possible to study the world around you and understand and make predictions based on those observations. Aristarchus is another good example of this. Aristarchus also lived in Egyptian-occupied, Macedonian-occupied Egypt, and he used the size of the Earth and the moon's shadows to determine the relative size of the moon and also the distance to the moon. He did this by using the knowledge of the solar eclipse. It was known to the Greeks that the shadow of the moon would taper down to almost a point when it reached the Earth. That's why very little of the Earth's surface will experience a total eclipse at any one time. He also noted that the shadow of the Earth, when cast on the moon, was about 3.5 times the diameter of the moon. Now, using these two measurements and the fact that he, like many of the Greeks, believed that the moon moved around the Earth in a circular orbit, was able to determine first from the location of the moon that shadow would decrease by 1 lunar diameter. That's using the information from the solar eclipse. And therefore, if the Earth's shadow was 3.5 times larger than the moon, the location of the moon must be a factor of 4.5 times smaller than the Earth. Once you know the size of the moon and the relative size that appears in the sky, it's very easy to determine its distance. So Aristarchus, again, made these simple observations, or took simple observations, and using mathematics came to a very important conclusion about our universe. Okay, obviously it wasn't a very large part of the universe as we know it today, but it was able to make an important measurement in terms of really realizing the scale of how far away even our closest celestial neighbor was. Finally, we get to the probably one of the most important of the ancient Greek astronomers, and that was Hipparchus. And Hipparchus was responsible for developing the first magnitude scale. And he, as we discussed in the night sky, ranked the stars on a scale of 1 to 5. First magnitude being the brightest, fifth magnitude being the dimmest stars that he could see. Of course, Hipparchus is also very famous for accurately cataloging the positions of hundreds of stars in the sky, and creating a catalog that was still used in the Renaissance because of its accuracy. Now, not all of the Greek philosophers contributed in a way that expanded our knowledge of the universe. Some of the best philosophers, and well-meaning as they were, actually impeded the advancement of astronomy. See, Aristarchus, who had measured the size of the moon, used geometry to also give an approximation for the size of the sun. The problem was, using trigonometry and the angle of the quarter moon and the sun, he didn't get a very accurate measurement. There's a great deal of uncertainty. But what he was able to determine was that the sun was significantly larger than the Earth. And because of this, he postulated that the sun being the largest object in the heavens, much larger than the Earth, that the Earth should go around the sun. Now, unfortunately, Aristotle didn't take this view. Aristotle correctly observed that the stars in the heavens had no parallax, or he couldn't observe any parallax. Later on, we'll see that you actually need very powerful telescopes to see this. Now, the reason why this is important is because if the Earth is moving, the position of distant objects should also shift relative to how close they are to us. And therefore, because of this, he ended up believing that the Earth is not moving, the Earth is the center of the universe, and developed this geocentric model. Well, he didn't develop the geocentric model as much as he supported the geocentric model. Now, again, without the parallax, Aristotle, thought that the Earth wasn't moving. He also believed in the idea that if the Earth did move, that because objects in motion need a force to push them, that everything would fall off the Earth if the Earth were orbiting the sun. So that also didn't make sense to him. And obviously, a geocentric model appealed to the ancients. It didn't feel like the Earth was moving, so why should we create a model where it is in motion? Now, one problem that did arise with this geocentric model was it was very difficult to explain the motion of some of the planets. Think about it this way. The Earth is at the center. The Greeks believed that all the objects in the heavens were on these concentric spheres. That made sense because, the moon, obviously, as know today, orbits in a nearly circular orbit around the Earth, so, that wasn't unrealistic to think that way. Again, the sun rises and sets in sort of a 24-hour cycle, so, placing that on a circle makes sense. What was of great difficulty to the ancient Greeks was this idea of the planets. Sometimes they'd go forward and backward in the sky. And just simply sitting on a sphere like this just was a very difficult way of explaining this, what we call forward and then retrograde motion. So another ancient Greek astronomer by the name of Claudius Ptolemy, who we know as Ptolemy, again, lived in Alexandria, Egypt. However, by this time, the Roman Empire had taken over, what used to be the Macedonian Empire. And Ptolemy tried to explain the problem of the retrograde motion where the planets would go forward and backward by saying that the planets themselves were on a slightly different structure than the sun and the moon. Again, moon very simple to explain, as it simply goes through its monthly cycle and its daily cycle. Same thing with the sun. It goes through its annual cycle and its daily cycle. You could explain those with those concentric spheres. But with the planets, Ptolemy saw that a more complex structure was needed, and he developed this idea of epicycles. Epicycle means circle on top of circle, and this very neatly explained the retrograde motion. And in science, we accept models if they accurately predict the reality. And the epicycle model that Ptolemy developed was, very good at predictions. However, we know it wasn't reality. So, Ptolemy was successful in one sense, that he developed a physical model of the heavens, and that the physical model accurately predicted things. However, obviously, it was not a realistic model in terms of what we know about the solar system today. Now, it was a very long time before anybody took up this question. It took over 1,000 years. And one of the main reasons for this is not a lot of advancement was made in astronomy during the time of the Roman Empire, beyond what Ptolemy had done. With the collapse of the Roman Empire in Western Europe, it left a huge vacuum in terms of government and also learning. And it wasn't until the Renaissance that people started having an interest again in questioning some of these old ideas. And somebody who questioned the work of Ptolemy was actually somebody who admired his work, and that was Nicholas Copernicus. Copernicus studied the Ptolemaic model. He had interested in the discipline of astrology, where people believed that they could watch the heavens and predict one's fate. Today we have a very crude form of this in the form of horoscopes. We know today that the heavens have nothing to do with what happens on Earth. But in 1473, he was studying the model of Ptolemy, and he found it very difficult and very complex. So Copernicus looked to find an easier way of calculating the positions of the planets. And initially he did just sort of a mathematical change. He didn't think that the sun was the center of the universe. But he tried to simplify his calculations by placing the sun at the center and simply putting the planets on these circular orbits. And what he found is that it worked. Again, Ptolemy's model was accurate in its prediction. The problem with it is that it sort of defies something we call Occam's razor. When presented with more than one solution to a problem, Occam's razor says that we take the simplest explanation. And that's what happened with Copernicus. By placing the sun at the center, it solved the problem that Ptolemy had, but with a much simpler model. Now, initially, the church, the Catholic Church, which was one of the largest powers at the time, and even those involved in the Protestant Reformation, rejected this idea. Without getting into deep theological arguments, it was believed that the Earth was the center of the universe, and they came up with this with convoluted arguments from the Bible. And therefore, Copernicus's publication, where he had the sun at the center, was seen as being heresy. Again, nothing in the Bible said that the Earth was the center of the universe, but theologians had accepted this and actually adopted this from the Greeks, who they considered to be pagans, So there's a little bit of irony in there. They were accepting something as a religious truth based on work that had been done by people that they thought were pagans or not believing the same things that they believed. In any case, it's interesting when Copernicus made this publication. There's a little bit of controversy here. He published it, out as he was dying, and the story goes that he knew that the church was going to come after him, so he didn't publish his works until at the end of his life. Others argue that he published it, and that initially it was published simply as a mathematical means of calculation by the editor who had changed Copernicus' work. Copernicus then made him republish it with the proper theory, saying that this theory indeed was reality, but by the time that the editorial changes were made, that Copernicus had died. Well, in any respect, if Copernicus had been alive, he would probably have been very severely punished by the church. And without the ability to punish Copernicus, the Catholic Church in Poland at the time was a very Catholic country, as it is today. The Catholic Church banned Copernicus's work, and it was you were not allowed to teach or even read this work. However, his work did go all over Europe. It did spread all over Europe, and it did get a lot of people thinking. About the same time, or a little bit later than Copernicus, a Danish nobleman by the name of Tycho Brahe began to study astronomy, and without going into long details about this very eccentric and very arrogant person, Tycho Brahe is really responsible for making observational astronomy popular. Very interesting person. He had a pet moose. Unfortunately, the pet moose was given to somebody on loan, and the pet moose got drunk at a party and stumbled down the steps and was killed. A pet moose. And Tycho lost his nose. I mean, if you'd seen him, you would have thought he was a rather odd-looking fellow. He lost his nose in a duel when he was a student fighting another student, and he wore a prosthetic nose made out of gold and silver. Extremely arrogant. In fact, the duel was over the fact that another student claimed that he was more intelligent than Tycho, and Tycho took great offense to that. He actually became the student's friend, even though the student ended up cutting off his nose in the duel. But in any case, Tycho came from a very wealthy family. His father had worked for the King of Denmark, and therefore, he had a lot of noble connections. And he was funded by the King of Denmark to build an observatory on the island of Hven. And this observatory was not so much an observatory we think of in terms of today with telescopes. Instead, it had quadrants, which were huge protractor-like devices that would measure the positions of different objects. And here's a view of a smaller quadrant. And again, it was simply there to measure the angle of stars and planets and determine where they were. Now, Tycho used the idea of parallax to try to determine how far away different objects were. And by measuring the angle at different points in the night, you can see if the object would shift a little bit based on, this parallax. The moon actually shifts a little bit in the sky as your position on Earth changes because it's so close to us. The planets, they do the same thing. So he's actually able to measure the distance to the planets and the moon and also the sun. And he came up with something that was very interesting. Tycho, for all his arrogance, knew enough perhaps not to challenge the church. Or maybe he just didn't feel that the Earth moved. But he came up with sort of this hybrid model, somewhere between Copernicus and Ptolemy. He liked the idea of the simple planets going around the sun, but he still wanted to keep the Earth stationary. So in his model, the Earth was the center of the universe. The planets went around the sun, and then the sun went around the Earth. And again, Tycho's problem with the heliocentric model was the same problem that Aristotle had, thousands of years before. Tycho had very accurate equipment. He can make very precise measurements of the stars, and he never saw parallax. What he couldn't imagine was the stars were so far away that even his instruments weren't sensitive enough to see that. But again, he preserved this ancient Greek idea that the Earth was at the center. But what he overturned was the ancient Greek idea that the heavens were unchanging. And the reason for this was he was able to observe two very unusual events: a supernova explosion and a very bright comet. And the ancient Greeks believed that the heavens were unchanging, therefore anything that we would see up in the heavens, such as a comet, a nova, which is a new star, star becoming brighter or dimmer, was not so much a celestial phenomena, but instead was something that happened up in the atmosphere. And today we know, for instance, meteors are atmospheric events. Aurora are atmospheric events. So it's not unreasonable to think that anything strange going up in the heavens was actually happening in the atmosphere rather than beyond the Earth. But Tycho clearly showed with his measurements that this very bright supernova, which appeared in 1572 in the constellation of Cassiopeia, he attempted to measure a parallax for it and showed that indeed it showed no parallax. It was beyond the atmosphere of the Earth. And this discovery strongly opposed the Greek notion that the heavens were unchangeable. Likewise, he also observed a comet, and comets were, again, thought to be atmospheric disturbances. The Great Comet of 1577 allowed him to make many, many measurements, and what he determined was this comet, in fact, was within our solar system, but well beyond our atmosphere. So, once again, Tycho, although he supports some of the basic tenets that were established by the ancient Greeks, he does, overturn, some of these other ideas that were, greatly entrenched within the astronomers of the Renaissance and before. So again, Tycho's contributions are really twofold. One, he makes the observational astronomy. He makes it more popular. He popularizes it. And number two, he shows that the ancient Greeks were certainly not right about everything that they claimed. Tycho's arrogance gets him in trouble. When King Frederick passes away, who had initially funded Tycho, Tycho fell out of favor with the new king, his son, King Christian. And, a lot of this was Tycho's fault. He had a chapel on the island where his observatory was built. As part of the funding, he was supposed to keep this chapel, which had been built in honor of King Frederick, in good repair. And King Christian either visits or has some of his officials visit the island, and they're just shocked by the level of disrepair of the chapel. In one respect, Tycho was so obsessed with his work he couldn't care less about other things like keeping the king happy. He was concerned with making observations. Why should he be troubled with keeping this chapel in order? Of course, in King Christian's defense, letting the chapel built in honor of his father to go into disrepair was of great disrespect to the king. So King Christian and Tycho get into an argument. Tycho says, fine, I'm the greatest astronomer there is, so I will just take my wares and go to another location where I'm appreciated. So they have their falling out. And Tycho goes to Prague, which is in the current day Czech Republic, but at the time was part of the Holy Roman Empire. The Holy Roman Empire, you know, if you think about today, included Germany, it included Czech Republic, and a few other places. At the time, it was governed by King Rudolf, and King Rudolf, the Holy Roman Emperor, was suspicious of Tycho. He wisely knew that Tycho had fallen out of favor with the King of Denmark, with the new King of Denmark, and he wanted some insurance that if Tycho had one of his little temper tantrums, he all the work that he did in astronomy wasn't lost. So he actually hired Johannes Kepler to be his assistant. And Kepler at the time was a good astronomer in his own right. And soon after Tycho died, soon after taking his position in Prague, Tycho dies, and it provides Kepler with the opportunity to look at a lot of Tycho's data that he'd taken on the planets. And that certainly led to a lot of advancements that Kepler made. Again, Tycho, as Rudolf was suspicious of Tycho, Tycho was suspicious of Kepler. Kepler was only allowed to see Tycho's data on Mars initially. And Tycho had hoped, because the Mars data was so confusing, that this would stall Kepler from making any important discoveries. And of course, Tycho dies, so there's not much that he can do to control Kepler at that point. So we'll put that story aside. Tycho makes significant contributions, but the irony is his assistant becomes even more famous than Tycho using his data. So we'll let that hang for a little bit. And we'll talk about Galileo, who was a contemporary of Tycho. And like Tycho, Galileo believed in observational astronomy. Unlike Tycho, he's really the first to use the telescope for astronomical observing. He spends most of his life, Galileo, providing evidence to support Copernicus' heliocentric model of the universe. And toward the end of his life, he was charged with heresy for supporting this model, because if you recall, it was Copernicus who published his work on his deathbed and therefore escaped being charged with any crime by the Catholic Church, by the Inquisition. Now, Galileo not only used his observations from the telescope, he also used observations in the laboratory. And what he did is he used an inclined plane to try to disprove this idea that Aristotle came up with, this idea that the Earth couldn't move because everything would fall off of it. And using an inclined plane, he developed this concept of inertia. He said, things don't need a force to keep moving. Okay? Things would move on their own due to this property called inertia. And this idea was that an object would keep moving due to inertia, regardless of whether it was being pushed or not. So, once again, Galileo has to, disprove what has been, established by the ancient Greeks. And he does this through experimentation. He says, you can't just deduce this thing, much like the Greeks would. The Greeks didn't like experiments because they viewed the world as being corruptible and imperfect. Galileo says, no, if you want to understand nature, you need to study nature. And his inclined plane allowed him to do this. Galileo also shows that the ancient Greeks are wrong. in terms of gravity, Aristotle had said that heavier objects would fall faster than lighter objects because they would tend to go to the proper place in the universe much faster. Galileo says, no, if you eliminate things like air resistance, you can see that all objects would fall at the same rate. Now, we have this view that Galileo was on the Leaning Tower of Pisa, dropping a heavy object and a light object. But no, he never did that experiment. Again, he used his inclined planes to show that light marbles and heavy marbles would go down and accelerate at a constant rate. Now, his most convincing empirical evidence came from the use of his telescope. Again, Galileo set out to show that the ancient Greeks were wrong about many things, and therefore they could be wrong about their geocentric model. And the ancient Greeks believed that both the moon and the sun were perfect spheres of light. And what Galileo was able to show, actually, they didn't believe that the moon was a perfect sphere of light. They believed that correctly that the light came from the sun. But they believed the sun was perfect. But Galileo saw sunspots on the sun using his telescope. He also looked at the planet Venus. And in his telescope, he watched it go through different phases. Now, if Venus went around the Earth, as the ancient Greeks had said and Ptolemy had said, you shouldn't be able to see all the phases that Galileo observed. And in fact, what Galileo had seen was, on its closest approach to the Earth, Venus became a very thin crescent. As it moved away from the Earth, it became nearly full. So this strongly indicated that Venus was not going around the Earth because it's getting very close, it's getting very far. Instead, it had to go around the sun. Also, Galileo had observed the moons of Jupiter. He saw objects orbiting something other than the Earth, going around something other than the Earth. This is a strong indication that the ancient Greeks were wrong. Finally, Galileo observed mountains and craters on the moon. This, again went against the fact that the moon was a perfect sphere, because these mountains and craters would cast shadows. And the ancient Greeks also believed that the physical laws of the heavens were very different from that of the Earth. The fact that they cast shadows certainly showed that this was not the case. Now, initially, Galileo publishes his work in a thing called the Sidereal Messenger. And he does this in 1610. And this is just a description of the observations that he made. This doesn't really get him in any trouble, but he does get in trouble later on when he begins to explain these observations. And he does this in the a book with a very long title, but many just refer to it as the Dialogue. And it's a very interesting work in that it argues different points from two perspectives. In the book, he has two people, one arguing the Ptolemaic system, where the Earth is at the center. The other one is the Copernican system. And the book's very witty, but it gets him in trouble, and he has to go before the Inquisition, where he is found guilty of heresy for teaching the Copernican system, which had been outlawed. Galileo is placed under house arrest, and his next work, The Two New Sciences, is actually published in secrecy, because Galileo is under house arrest, and he is closely watched by the Inquisition at this point in his life. Galileo is buried. He's buried in secrecy initially because of his problems with the church. Eventually, he is transferred to the family tomb, and this doesn't take place until much later. He dies in 1642, but his body's not transferred until about 100 years later. So Galileo provides experimental evidence to support the Copernican model. This is very important in science. We don't accept theories unless we have empirical evidence to support these ideas. That's the whole essence of creating a scientific theory. And although Galileo's work, like Copernicus's work, is banned by the church, Galileo is successful because people read it despite the ban. And eventually the church has to relinquish its position in terms of banning his works and other works on the heliocentric system. And astronomy is able to advance despite the religious objections. Now, going back to Kepler, Kepler also was, alive during the time of Galileo. But Kepler is further from Rome, the Vatican, of course, which was the center of the Catholic Church. So he had a little more flexibility. He did live in the Holy Roman Empire, and he studied the Copernican model while at university. And, like Galileo, like Tycho, he was a very gifted mathematician. And like Galileo, he's also very religious. Now, Kepler made very important discoveries in optics and mathematics, but again, he's best known for his model of the solar system. Now, initially, he thought that the solar system was constructed in such a way that the spacing of the planets could be described in terms of these geometric solids. Things like the tetrahedron, the cube, the octahedron, the dodecahedron, and the icehedron, that if these were embedded within spheres, that the spacing of the planets would naturally come from the spheres. But of course, this model was later seen as not having any basis to it. Of course, Kepler becomes the assistant to Tycho and begins to work on Tycho's data, and has great difficulty with Mars. I can't understand why Mars's data doesn't seem to make sense until he realizes that Mars isn't going around the sun on a circular path. Mars is going around the sun in an elliptical path. And when he reconciles this, he develops his three laws of planetary motion. Now, although these three laws didn't provide an explanation of why, they did allow us to better understand how the planets went around. His first law said that the planets went around the sun in elliptical orbits. The sun is centered at one of the focuses of the ellipse, or foci, and the second focus is unoccupied. Again, this changes the Copernican model, because in the Copernican model, even Copernicus had to have the planets on small little epicycles going around the sun to explain some of the deviations in their movement. The second law is a highly mathematical law, but it basically said that a planet would have to sweep out an equal area over an equal time period as it went around the sun. We know this is true today because the planet, as it gets closer to the sun, feels a greater gravitational pull. So it has to speed up in order to sweep out the same amount of area. Finally, the third law said that the distance that the planet was from the sun to the third power is related to the time it took the planet to go around the sun to the second power. And this, of course, became very important later on, even though Kepler didn't understand why this mathematical relationship took place. It took Sir Isaac Newton really to explain these mathematical relationships that Kepler had discovered. Newton is born in 1643, about 1 year after Galileo dies, and Newton discovers very important laws of motion. He discovers the universal law of gravity. He invents calculus and even makes important discoveries in optics. Newton is a very troubled individual, especially at the beginning of his life. His father dies before he is born. His mother is forced to remarry. And Newton, not being a product of the second marriage, is rejected by his father, is forced to live with his grandparents. Initially, he's not a very good student, but eventually his teachers recognize his brilliance. He is encouraged to go off to Cambridge University, and is so successful there that they hire him to become a professor. From there, Newton's contributions are quickly recognized. Not only is he promoted to the position of Lucasian professor, that's sort of the head of the math department at Cambridge, he eventually becomes part of the Royal Society, which is a very elite group of mathematicians who decide important issues of math and science. His greatest work, the Principia, is published in 1687, and this is sort of a culmination of all his mathematical and physical work. And Newton becomes so popular, he actually becomes a member of Parliament at one point, sort of the equivalent to our Senate and House of Representatives in the United States, and heads up the Royal Mint. Newton is also credited with inventing the reflector telescope, the basis for most research-grade telescopes that we have today. In fact, if you look at the Hubble Space Telescope, and you look at large telescopes like the Keck, which was, until very recently, the largest telescope in the world, both of these are designs based on Newton's idea of a curved reflector at the back of the scope, and then a detector, an eyepiece at the front. Now, Newton's laws of motion build on some of the work that Galileo did. The first law is essentially Galileo's law of inertia. An object at rest tends to stay at rest, an object in motion tends to stay in motion, unless acted on by a net unbalanced force. It's basically saying that objects will move even without a force. A force simply changes the motion. And the second law says that the force acting on an object, the net force, is proportional to its mass and its acceleration. The more massive something is, the more force it needs to get it to accelerate for a given amount. And finally, Newton's third law is probably something that you're very familiar with. For every action, there's an equal and opposite reaction. That when we push on something, an object will push back on us. Now, Newton comes up with his universal law of gravitation, partly with the work that Kepler had done, and partly by comparing the motion of the moon to a falling object. The story goes that Newton was sitting in his family orchard one day and observed an apple falling. He looked up in the sky and he saw the moon, and he was well aware that the moon goes around the Earth in a nearly circular pattern. And anything going around in a circle, Newton was well aware of, requires a centripetal force, meaning a force pulling it toward the center. He quickly realized that the apple falling to Earth and the moon orbiting the Earth were both being controlled by the same force, gravity. Now, it's important to note here that Galileo was able to calculate the acceleration of the moon and saw that it was much less than that of objects falling near the surface of the Earth. And that told him that gravity actually decreases with greater distance. And that's how he came up with his universal law of gravitation equation. That says that the gravitational force is the product of the two masses pulling on one another. It's Newton's third law. For every action, there's an equal and opposite reaction, divided by the distance that separates them squared. Had to explain why the moon felt a weaker gravitational pull than, say, the apple, for its mass. So Newton comes up with the universal law of gravitation, and this has very large implications for not only the moon going around the Earth, okay? It explained the moon's orbit. It also explains the orbit of the planets around the sun. Now, Newton wasn't aware of this, but we now know today that Newton's universal law of gravity also explains how our Milky Way galaxy is held together, and even the overall structure of the universe. When Newton dies, he's recognized for his great accomplishments. This is very unusual for a scientist. Many scientists are not appreciated until after they pass, especially mathematicians during Newton's time. Galileo had not been appreciated fully until he had long passed. But he, during his life, he was knighted by the Queen for his works in mathematics and science. He dies in 1727 in London after his health is deteriorating for quite some time. He's one of the few people of non-royal lineage who's buried in Westminster Abbey. And it's said that he received a burial fitting for a king. So, that was really, indicative of how much Newton was appreciated by his country at the time. He was a celebrity in England, as opposed to Galileo, who sort of buried in secrecy and in disgrace in his own country. So in terms of summarizing our contributions, we go back to the ancient Greeks. We credit them for changing astronomy in terms of developing a physical model of the universe rather than, a mystical model. Yes, their model is incorrect in that they say that the Earth is the center of the universe, but at least it gets the ball rolling, and they sort of show the way and show the connection between math and what is happening in the heavens. Ptolemy, of course, uses epicycles to explain the retrograde motion of the planets. So he accurately predicts motion, even though his model, again, doesn't necessarily represent reality. Copernicus, he publishes his sun-centered supporting model of the universe. Tycho Brahe makes important measurements showing that the heavens do change with time. And Galileo uses empirical evidence to support the Copernican model. It says here, evidence for the geocentric model. He provides evidence for the heliocentric model. So sorry about that. Kepler furthers Galileo's work, publishes the 3 laws of planetary motion, which describe how the planets work, move, not why they move, and Newton puts it all together. This universal law of gravity explains why the heavens move the way they do. Okay, well, that's it for today's presentation. I'm going to wrap it up, and I will see you for the next one.